Hello students, myself Professor Ankur. I welcome everyone for the GATE sum session on analog circuits. Today we are going to solve important sums on the topic of negative feedback. This is our third sum session on negative feedback. Let's start with the sum session now. So this question is from the GATE 2010 paper. It has come for 1 mark. Let's have a look at the question. The question is, the amplifier circuitry shown below uses a silicon transistor. So let's have a look at the circuitry. So this is a circuitry. The capacitor CE and CC can be assumed to be short at signal frequency, and the effect of output resistance RO can be ignored. If CE is disconnected from the circuitry, which of the following statement is true? Option A, the input resistance Ri increases and the magnitude of voltage gain AV decreases. Option B, the input resistance Ri decreases and the magnitude of voltage gain AV increases. Option C, the input resistance Ri decreases and the magnitude of voltage gain AV decreases. Option D, input resistance Ri increases and magnitude of voltage gain AV increases. So if you observe the figure carefully, you can see the transistor in common emitter configuration with input is given to the base terminal and output is taken from the collector terminal, and we are shown a coupling capacitor CC on the input side and the output side, and a bypass capacitor across RE. So the question is regarding what will happen if I eliminate CE from the circuitry. It is as good as the bypass capacitor is now vanished, implies it is absent in the diagram. So with this, what will be the impact on gain and input resistance? So for that, we need to understand a small thing. So this becomes the AC equivalent when we go for absence of the bypass capacitor. So we have the transistor in terms of R pi and GM pi, the output resistance RC, input point RB, and a voltage source Vs. And at the emitter end, we will have RE now. So what will happen? The input resistance will become R pi in R pi plus 1 plus beta times RE. I repeat, due to the addition of RE now, because the CE is eliminated, the input resistance will become R pi plus 1 plus beta times RE, implies the input resistance will increase. And what will be the impact on gain simultaneously? When I talk about the gain value will become GMRC upon 1 plus GMRE. It is as good as the original gain, which was GMRC, will now have a factor in the denominator, which is 1 plus GMRE, implies the original gain got reduced by a factor of 1 plus GMRE. So hence we came to a conclusion that input resistance will increase and the gain of the amplifier AV has to decrease. Hence the correct option is option A, which mentions input resistance increases and magnitude of voltage gain decreases. Next question. This question is from the GATE 2004 paper. It has come for 1 mark. Let's have a look at the question. So this question is regarding a good current buffer. The question says a good current buffer has option A, low input impedance and low output impedance. Option B, low input impedance and high output impedance. Option C, high input impedance and low output impedance. Option D, high input impedance and high output impedance. So first of all, we need to understand what do you mean by a current buffer. All of us are aware regarding a concept defined as voltage buffer. What was actually a function of buffer circuit? The buffer circuitry has always a gain of 1. So what is its duty? Whatever is the input energy, you pass it to the output side. So if it is a current buffer, the input current should be passed to the output with minimum losses. So for this, we need to first understand what do you mean by the buffer circuitry. So let's check. So this is the ideal buffer circuitry which will accept the input current and there is no input resistance. So it is as good as whatever was the current given to it, everything was accepted with zero internal resistance. So the output current I out will be K times I in. So this is the logic of ideal buffer. But when we go for a practical buffer, the practical buffer at the input side will have an input resistance Ri. And since we are having a current source at the output side, a current source always has resistance in parallel. So now we have a small understanding that if the current buffer has to accept the current, it has to accept maximum current with minimum possible opposition. So the Ri value has to be low. And whenever the current has to be given out to the next circuitry, it has to go for minimum losses. So for that, the RO value has to be very, very high. So the correct option is basically the current buffer should have very low input impedance and very high output impedance. So this is the basic understanding regarding a good current buffer. So the answer is option B. Let's go for the next question. This is again from the GATE 2014 paper. It has come for 1 mark. Let's have a look at the question. The question says, in the AC equivalent circuitry shown in the figure. So let's have a look at the figure. So this is the figure. If I in is the input current and RF is very large, then the type of feedback is. So if you observe the figure carefully, there are actually 4 options given. I'll read out the options first. It is voltage feedback, voltage current feedback, current voltage feedback, and current feedback. So always remember one important point, the definition of the type of feedback. Like if you remember voltage series, voltage shunt, current series, current shunt, the first term was always indicating what element you're picking up from the output side. And the second element was indicating the way in which you are mixing it at the input side. So this is a small hint or understanding to figure out which type of feedback it is. Now coming back to the circuitry, if you observe, you are having an output node V out, which is direct link RF on the input side. So we are having an input current source defined as I in. So the current coming from the current source will be splitting. So now the main thing we need to understand here is that the output is basically taken at the drain of the second MOSFET, and it's a direct link with the help of RF to the source of the first MOSFET. So the main thing we need to understand here is it is voltage sampling. The second thing we need to understand here is it is shunt mixing. A current source with a node on the input side indicate that it is shunt category type mixing because the input current will split into 2 parts. So with that concept, we can easily understand that it is voltage current feedback circuitry because you're sampling voltage from the output end and the mixing happens with respect to a node. So it is as good as current mixing, and hence it is voltage current feedback circuitry. The answer is option B.